Hey, good morning, everyone. We want to welcome you to today's Voxelmaps webinar focused on 4D models and the transportation sector. We have with us today Peter Atalla, our CEO, who's going to be a part of the presentation with myself, Brian Soliday. We want to welcome you. A couple of things. If you have a question for us, please provide that the question via the Q&A button at the bottom of your screen, so you'll see that. And then just an FYI, we are recording this session and we'll be providing this to everyone after the event. And we ask that you please feel free to pass that along to your colleagues that couldn't make it today. So with that, I'd like to talk a little bit about what we're going to be presenting. So we're going to start today with just an overview of Voxelmaps. And Peter's going to share with us the whole concept of maps for machines and then get into talking about volumetric mapping and what that really means to us within the Voxel world. Speak a little bit of time talking about data collection and how we do data collection for our projects. And then I was going to talk a bit about our initiative called the 100 Cities Project that we just recently kicked off. Then talk about some of the right-of-way and transportation use cases and some of the capabilities and areas where the technology is being used across a number of industries. I'm then going to share with you some of the highlights that we pulled from the U.S. Senate infrastructure bill. And so we're going to be providing you with some more detailed information about that in terms of a white paper, given that the bill itself is very, very geospatial and very infrastructure oriented. Everyone on this call should be very interested in that. And then we'll close it out with a number of questions. So with that, what I'd like to do is hand it over to Peter Atalla. Peter's the CEO of Voxelmaps. Go ahead, Peter.
Thanks, Brian. Really appreciate that. Good morning, everybody, or good afternoon, depending on where you are in the world. Thank you very much for taking the time to join us today. And you know, we were hoping to share a little bit about Voxelmaps and what we do and kind of the applications of the technology. So let's get started then. By way of giving a little bit of background on the company, Voxel's been going for about 4.5 years, but actually it was a spin out from an existing mapping company called Navme. Navme was based actually in the UK, but actually became quite a big mapping company. We mapped 180 countries around the world, which is almost the whole planet. It was a huge project, took about 10 years, collecting about 7 billion kilometers of data and involving tens of thousands of people. But we had a division of that business that was really focused on what should the future of mapping be like. And so we decided to separate that out, and that became Voxelmaps, and we've been kind of separated since. In terms of our location, headquarters is in San Francisco, but we have a number of offices around the world, Mexico City for Latin America, the UK and Portugal covering Europe, and then we have Singapore and Sydney, Australia as well. So we're about 350 people or so, growing pretty quickly at the moment. Now, Brian mentioned in the introduction the concept of maps for machines. And so I want to take a few moments just to kind of explain what we mean by that. So human maps, I'm sure we're all very familiar with. These are the maps that are in our mobiles, on our phones and cars and computers, web, etc. And they're mainly around a use case of navigating people to an address, be that a street or a building or a city. The secondary use case is really around visualization. So, you know, taking some form of geodata and putting additional layers on top of maps. The majority of human map data is 2D. There are some 3D elements, but it's not extensive yet. And it's pretty low resolution stuff. So we're talking 1 to 3 meters in terms of accuracy. And that's fine for humans because we can decide where we want to walk, where we want to drive. But when we start looking at machines, the requirements are very different. So really a machine level map is a true spatial 3D model of everything that we see in a given environment. So in cities, we're analyzing many different types of objects. That's everything from clearly the buildings, the roads themselves, but infrastructure, telecoms, utilities. In non-urban environments, that can be vegetation, land structures, land classification. And we're doing this at very high resolutions. So we're talking 1 to 4 centimeters in terms of resolution. So imagine just creating a map to that kind of resolution. There's a lot of possibilities. So with this kind of map and model, we're not just looking at the location of objects, but also different features of them, the measurements, the attributes of the objects that we're looking at. And then when we talk about machines, it's everything from computer models and artificial intelligence to better understand cities or different types of environments, all the way through to new forms of autonomy, be that autonomous vehicles, delivery robots, AMRs, which are automated miniature robots, even drones as well. And there's a requirement for this data in this model to exist everywhere. So outdoors is definitely one of the biggest use cases, but there's a requirement for indoor data, for subterranean data, even in the future, ocean data as well. And there's some interesting stuff around that. So I want to start really by explaining then the approach to how we build these maps. And really it's around this concept of volumetric mapping. So I want to sort of compare and contrast standard 3D and then a volumetric approach and just explain the difference. So this is an example of a 3D map. This is from Google, but there's other alternatives here. Apple, for example, have these maps. And these are great visualization tools for humans. They look very pretty, they look like the city, but in reality, these are very low resolution structures. So when we zoom into the structures, we start to see a very basic mesh object with some kind of texture over the top. Again, for visualization, it's absolutely fine. But if we were to perform measurements and calculations from it, it's too low resolution. It wouldn't suffice. The additional problem with this kind of technology in terms of meshes is that there's no interior information to the mesh. And so, if we went inside there wouldn't be anything else there. And so that's really because meshes are focused on one aspect of physical matter, which is the surface information. But in reality, the interior information when it comes to mapping is very important as well. One example of this is if you're looking at the brain, if you're scanning and mapping the brain, you don't do that in meshes. You do that using a volumetric approach because the interior information is incredibly important. So that's what we do really at Voxelmaps. We build a volumetric model of the planet. And so the way that we do this is using voxels, which I'll come and explain what those are. But essentially using this approach, it allows us not only to map the surfaces of everything that we see, but also the interior information as well. And that's very powerful when it comes to updating the maps and making sure that we have a model whereby we can collect data and automatically have the data drop into the model without having to do a lot of pre-processing involving humans to make that happen. We also add a fourth dimension of time. And this becomes very powerful for change detection. And I'll show you some examples of that as we go through the presentation. So how do we do this? The approach that we take is using voxels. And voxels are just 3D pixels. Essentially, they're cubes. This isn't necessarily a new technology in terms of voxels themselves. They've been used in things like computer games for a long time. So Minecraft is an example of a voxel rendered world. And as I mentioned, they're also used in things like brain scans. But actually what we do is we use an approach that first was developed in robotics. And it's using voxels in a configuration called a VOG, or a voxel occupancy grid. The use case here would be that there would normally be a small robot with some kind of 3D sensor on the top, maybe a LiDAR, and it would go into a room and it would produce a very basic 3D matrix, essentially, of the room, so it could navigate its way around. So we took this idea, but we applied it to the entire planet. The technology is something called an MRVOG, a multi-resolutional voxel occupancy grid. So we took the Earth and we placed a mega voxel, a giant voxel over the entire planet. And then this voxel is full of multi-resolutional voxels. Theoretically, they can be any size, but for our purposes, we use 8-meter voxels down to 1 centimeter voxel. Now, this matrix of voxels goes straight through the Earth. It's what we call an Earth-centered, Earth-fixed reference frame. And because it's everywhere you're sat at the moment is full of these virtual voxels. Each voxel has a permanent position in space and has a unique address, a machine address. But to start with, it's blank. It's just a reference system. There's no information in it. So what we need to do is we validate the occupancy status of the voxel. Basically, is the voxel in free space or is it in matter? So we do this using LiDAR. If the laser beam from the LiDAR passes through the voxel and it's not reflected off anything, we say this is free space. But the moment that it's reflected off a surface, we label this as occupied. And so what we're doing really is etching out the matter of the planet in this way. But the fact that this is a global structure that we have here, really what's been created is this global spatial database for 3D and 4D data. It's real time, it's persistent, so it's always on, it's always there. And it's designed to handle planetary scale, so thousands and thousands of petabytes of data. It's also integrated directly as well with 5G. So as that becomes enabled in the future, you have the ability to do real-time updates to the model as well. Now, there's some other really interesting benefits for using this approach in comparison to using points in 3D or meshes in 3D. So firstly, each voxel is a volumetric measurement unit. So it's very easy to perform calculations within the space. Secondly, on the surface of the voxels, we can put layers of additional information. So typically this can be from cameras, things like RGB values, for example. It could be hyperspectral imagery. It could even be radar. So with the voxels, we have the shape of things. With the surface information, we have an aspect of color. And then we can apply artificial intelligence in terms of deep learning models to look at these collections of voxels and recognize what they are in 3D. It's a true 3D semantic segmentation, not just a 2D pixel-led semantic segmentation. So the performance of recognition is much, much higher and has the ability then to recognize features and automatically extract those features. Now, it can do this in 3D, but it can also do it in 4D. So every voxel has an infinite number of time states. So it has a temporal data component. So we can get the AI not just to look at what's currently there, but also look at past data and compare the two. So we can do change detection, which becomes a really powerful tool. And so when you combine this with the permanent addressing, the global spatial database, the ability to intelligently search and pull back information, it becomes an incredibly powerful platform, kind of a superior platform really for building digital twins and digital twin technology. So I have a video here that I'd like to show you, and this just shows real data. So actually collecting data. This is from San Francisco. We'll start with just the occupancy data alone. So these are all voxels, this occupancy. And then we layer on the camera data. So we get this aspect of color. And once we have that, we get the AI to start doing the recognition. So all these pretty colors you see here, these are automated recognition events, which then can be vectorized by the data, by the artificial intelligence. At this point, we have the ability to play around with the data. We can export any set of features into any format, or explore things in different ways. And currently, the system is trained to recognize about 100 different assets in cities. We'll be up to about 200 assets pretty soon in the next couple of months. And we have the ability to train it on, if we have a customer that has a new type of asset, then it's a pretty simple process for us to go through and train the networks to recognize that feature. And then it can run across the whole of the data set and pull back that information. We're also doing this indoors as well. So it's not just an outdoor use case. We're actually training up the networks as well to recognize common features in indoor settings. So that brings me on really to this platform, this Insight platform. So all of the, what you just saw when the AI recognized the features and vectorized the data, that's powered by what we call the Voxel Insight platform. So this, what you can see here essentially is screenshots from the platform. And you can see the different colored lines and colored boxes. Each one of these is a recognition event. So it's recognizing an object automatically, but it's also performing the calculation. So from this interface, it's possible to export out into any other formats. So you can export into formats or applications that you're used to using, but also we collect, process, and store in voxels, which is a much better, more efficient way of doing that. From this interface as well, you have the ability to explore the data. So you can do virtual surveys, you can perform calculations within the space. You can even put a virtual reality headset on and walk around the data in the cities as well, should you wish to. We have a number of other tools which make the whole process and the data very accessible. So there's online web versions, so you can access the data via the web. We also have the ability to provide you guys the training set, so you can actually train the AI to recognize different features. Now, we can do that entirely for you, but some customers also like to do it themselves. So this is just an example. This is actually a web-based solution. And you can go into data and you can start training. This is a process called annotation. Here, the person is annotating trees. And so you train the networks to recognize the features you want. And once it's trained to a sufficient level, then the networks can run across all of the data and extract those features that you're looking for as well. So that's really the underlying technology. That's the data model, the advanced artificial intelligence to power the insights. But let's talk a little bit about the data collection side. So the way that we collect data is by using a sensor that we developed called Symbo. And these sensors have really been designed to do large-scale mapping projects. So one of the key things was about mobility and logistics. So this sensor can be installed by one person. It takes them about 10 minutes to do the initial install, and thereafter about 5 minutes to put on and to take off. At the end of a mapping day, you can take it and put it back in a Pelican case, store it in a hotel room. It doesn't need to be permanently affixed to the car. It also doesn't need to have a computer in the back of the car. In this platform, it has full edge processing. So it's running very powerful graphic cards inside, which process all of the data. So the platform consists of LiDAR, cameras, high accuracy GPS and IMU, the ability to use RTK and PPK for corrections, and also 5G signal as well, if we want to offload the data. You have the ability to offload either using hard drives or using 5G if 5G is available, or even Wi-Fi. So we have two ways that we approach working with customers. One, we can do projects end-to-end, so we can provide our vehicles, our sensors, people, and we map the particular areas for the customers. Or some customers like to have their own system, and in which case we provide the technology to them and then do the processing and obviously support through the process. We also have a new version of the Symbo, which is due to be released in September, the end of September. This is using dual LiDAR. This is particularly useful for taller buildings. You have the ability to angle the LiDARs and scan much higher up structures as well. The rest of the platform is pretty similar to the existing one, so it's very useful. In terms of the operational use as well, it's not just about providing your hardware and going away. We have a bunch of tools which make it easy to perform mapping missions. So the starting point is a mapping mission planner. It's an online application where we can take data for a city or even an entire country and break it down into daily mapping missions for operators. And then those mapping missions can be assigned automatically to the different operators. On their iPad, they see the jobs that they have to do for that particular day. And it can even direct them as well, kind of increase the efficiency of doing that mapping project and the mapping collection. What they see when they're logging in, once they've accepted a mapping job, is a very easy to use interface. You see a map which keeps track of where you've been. It kind of leaves that trail on the map. You see the status of the device. So if everything is green, it's all working very well. If something's red, then it allows you to troubleshoot. We even have the ability to remotely connect to the devices as the devices are online and troubleshoot if there's issues. One of the other really nice features here is it gives you real-time feedback in the mapping process. As you see the trail when you're mapping, if it's green, it means everything was working well. If it goes amber or red, then there's problems with the data. And it's better to alert the operator there and then so they can redrive that area versus discovering that in post-processing weeks later and then having to go back out and collect the data again. So it's really designed to make it very easy to use for people to collect very high resolution mapping data. So some of the benefits, why do this? Well, firstly, it allows you to map much faster than the majority of traditional approaches as well, and take some of the headache out of existing mobile mapping solutions if people are using them, which can be very cumbersome, expensive, difficult to deploy, a lot of calibration and setup. All of that has kind of been removed. When you're building then data into this digital twin, you're mapping everything. Even if you're only just interested in one asset, you're actually collecting the data for everything. So you have the flexibility to pull out additional features at a later time that doesn't need to be another mapping mission. You have all of the data fundamentally there, so you can pull those assets out. And by doing this, by creating a platform that's easy to use with one person operating it, it reduces costs. It's very easy to deploy, very easy to scale up and do large-scale country-wide collections using something like this. And as I said, mapping everything is kind of a key part of what we do at Voxel and building out these digital twins. The last thing I want to talk about today before handing over to Brian, who will talk about some of the use cases of this technology, is to let you know about a project that we're working on at the moment, which will be available soon. So this is what we call the 100 cities model, and it's a data as a service model. So this is where we're going actively and mapping 100 cities, the top kind of US metro areas around the country. And that data will be available around Q2 next year. And instantly you can use it off the shelf, you can access it online, use it for extracting features, for doing all the kinds of mapping and survey activities. This data set includes the full 3D voxel map and the 4D elements as well, plus the LiDAR point cloud information, the high resolution imagery, the road networks by the functional classes, and obviously the vectorization. So all of the data automatically, we're not just collecting it and leaving it in raw data format as well. We're also doing all of the vectorization, all of the attributes, all of the feature extraction as well. So if you're just interested in certain features, we can extract those. And just to give you an idea of what it looks like, this project is already underway. So this is out of the Bay Area, some of the data collection. This looks like it's an aerial view, but this is obviously ground-based collection. So you can see very clearly the roads, the infrastructure. As I mentioned, this is all pre-segmented, pre-vectorized as well. So you can pull back, again, all these different colors is the AI doing the automated recognition. Another example of this where we've got a lot of wires, for example, utility infrastructure here. Again, this is all being captured to high resolution and automatically extracted as well. So again, it's a very useful data set that will be available for people and customers to use. With that, I'd like to hand back to Brian to talk through some of these real world use cases.
Thanks, Peter. All right, so what I'd like to do is talk a bit about real world applications and use cases. And really there's a really broad capability on and across industry sector use cases that we can support. And so this kind of gives you an idea of, the areas. So it's like I said, it's pretty broad. It's, GIS and asset inventory. It's, roadway monitoring. It's identification of curbs and gutters, or ADA compliance on curbs, or public works or virtual design. So it's a pretty broad base of what we can do and where we have supported customers. And that's kind of what I want to talk to you about today. This is a use case of mapping of traffic signs. So within the road network right away, we were contracted to drive an area and do a feature extraction of the signage inventory, basically do a signage inventory within that right of way for a major navigation company. And so across that network that we drove, we identified and mapped out for them over 7 million signs. So a pretty significant amount of effort to do that. We did the automated sign recognition, and then all that data was then converted to XML for delivery to them. Installation compliance is another area. So this was for a local government. So we drove a number of the streets within a local government. We had an existing database, so we could do change detection on existing assets to see where compliance was in compliance, or the installation was actually in compliance based on the contractor doing that installation. We could do that. We did the automated feature recognition, automated measurements of the assets as well, and then again, identification of the areas where there was non-compliance. Another area, and especially probably near and dear to the hearts of many people sitting on this call, is a road network mapping. So we did a significant project for road network mapping for a major automotive company. In this case, we did a creation of HD maps for autonomous vehicle and feeding that data into the vehicle. We created the road lane models. We identified traffic signs, extracted striping, and a number of other features. In terms of city infrastructure, so this was a project that we did where we actually did automated asset mapping, so extraction, but we also utilized other content that the customer had. So we took the data the street level mobile collected data and merged it with some 3D models that they had previously acquired as well in terms of the high-rise buildings in that upper right. And so from that, we were able to create this digital twin of the city, and then went through and did the automated feature extraction of a number of assets, being the roads, road furniture on the right of way, utility assets in the right of way, vegetation, things such as that. So pretty broad base. So this just, again, some of this data was collected by us, some collected by the customer. Really, in our case, we're really data source agnostic in terms of using the Voxelmaps technology, the 4D volumetric technology, and the VAM software system as well. There's also a lot of capability in the area of airport and railway infrastructure. So, on the railway side, we can quickly perform measurements of the track and the topographical and surrounding areas of a railway path, identify vegetation encroachment as well, especially on electrified rail lines, and identify any issues that may be happening after a major storm, where you want to basically drive the network and see where you may have washouts that could cause problem to the integrity of the network. On airports, LiDAR is being used today to capture features in the airport. So a number of features, buildings, hangars, other objects, and again, both external and internal digital twins of all the facilities. As Peter mentioned before, being able to maybe drive the external features and then import the data of the internal into that model is a much easier task using the Voxel technology. Transportation accident studies. So, ground-based LiDAR can be used to capture the accident and crime scene. Can be used to quickly record the scene instead of using traditional survey methods. We're seeing people use that today. And this kind of allows, come in quickly, scan the area, and get out of there to get the traffic flowing. Flowing smoothly, especially in areas where there's been a loss of life, because those tend to take a lot more time for accident scene recreation. Some of the current challenges and future trends within this as well. So, we believe and know that mobile LiDAR has a huge potential for road inventory, primarily due to its improved safety. So it's somebody in a vehicle driving, not somebody out on the road, with a camera or a handheld LiDAR or a terrestrial LiDAR. It's already very flexible, and the data reusability as well. So what we have found is our customers in the transportation space, we do the collection. They may be only interested in the roadway, but in 6 months they may be interested in some development in an area, and they need to know what's in the right of way, sitting out a couple hundred feet. And so the data is there for them to use for further processing, further analysis down the road. LiDAR is an active remote sensing technology, and it really provides highly accurate 4D models with high point density. So again, being able to go back and do collections using that fourth dimension of time, and being able to identify areas of change within the transportation infrastructure. And then, what we see in the future is that, the whole mobility, the area of mobility, and whether it's us walking or driving in vehicles, is probably the area where I see one of the biggest impacts of LiDAR in terms of having autonomous vehicles continually being monitored and continually collecting data and providing that to sources that are doing, real-time assessment of the road network, the roadway characteristics, the surface terrain, assets within the right-of-way, et cetera. So we continue to see this to be a pretty significant growth area for anybody within the transportation space. In the urban area as well, so urban planning and digital twins. So, digital twins is a very popular term today, but it's incredibly useful in having a digital twin of every feature, and that's really the focus of Voxelmaps is to create this digital twin of the planet. That's why we're involved in activities such as the Earth Archive. That's going out and doing data collection in areas that are only accessible via airborne lidar. But within the urban planning, so disaster management, response, and recovery. So post-event, if you already have a digital twin of an area, you can quickly determine how much damage was done post-event via mobile lidar or airborne, right? Construction monitoring, which is a really popular area, monitoring where activities happening either along a roadway or other infrastructure like bridges, et cetera. Updating city base maps, or historic preservation is one of the areas that's really popular. That's why the Notre Dame Cathedral, it was a really good thing. They had created a 3D model of that in a digital twin, so that after it burnt, was extensively burned, they were able to go back and recreate that and create the models to rebuild to its original historic levels. In the smart city world, there's a lot of areas that, in the transportation departments at the local level can be involved in and use the Voxelmaps technology. So in terms of traffic monitoring, what you're seeing is, you can monitor, well, the good thing about LiDAR is it works both day and night. So you can monitor traffic both day and night. The vehicles themselves that have not Voxel, but LiDAR technology can do automated collection. They can identify vehicle types, and it really helps smart cities, gain a better understanding of where their traffic issues exist and why. And then on the area of security management as well. So, being able to identify and tracking people and assets and vehicles, and you can fine tune the LiDAR for alarm perimeters as well, and help meet the needs of the private or the public assets in the building structures themselves. We've also seen a lot of our customers in the area of having us create maps, doing the collection and creating maps for autonomous vehicles. So in this case, driving a limited access highway, being able to collect not only the roadway and the right of way, but extracting, striping, any feature, within there, all the road furniture, guardrails, signage, and then performing automated measurements on all those features as well. So not only identifying them, but then identifying the measurements of those and then extracting them and putting them into a vectorized format for use in other systems. So our customers find that incredibly valuable. Another area in autonomous vehicles, what we're seeing is that the vehicles themselves are becoming collection networks as part of this whole IoT infrastructure, and they could replace some area collections. They provide a lot of very detailed content, and then this whole concept that Voxelmaps is promoting, called the constant collection network, where you have LiDAR and cameras on vehicles like service vehicle fleets that are continually collecting data and providing that to a central source for processing and updating of a collective base map. Right? And also the whole with the whole smart cities concept is this whole vehicle to everything. So vehicles will be connected, to a number of different devices and applications as they're driving to support things like smart parking, right? So, the V2X vehicle to everything LiDAR could identify open spots for parking. I read an article last week that said there's 4 parking spots for every vehicle in the United States. And I don't know about you, but every time I go to, a shopping area, a lot of them are tough to find a place to park, and this could help in that manner. Also, an area that I'm seeing a lot of interest is in performing geometric assessments of the roadway. So using collecting data and then doing highway attribution, such as sight distance, stopping sight distance. So, you've got groups that can consume LiDAR and have applications to do that, like RDV systems, that, as you drive a roadway, it identifies areas where you have limited sight distance, so you need to slow down, right? And I really feel that, as people continue in the transportation sector continue to use LiDAR, that there's going to be this paradigm shift in actually using that geometric assessment and safety audits and how they're used by DOTs and local transportation organizations. And, despite this whole huge potential, there's been limited research in that particular area. So I don't know if any of you were involved in the geometric design, but that's an area where, there could be significant opportunities for growth. So this is showing a example use of our Voxelmaps indoor visual positioning system. And so I will start this, and I think Peter's going to describe what's going on in this video.
Yeah, actually, just before you started, Brian, let me just explain what we're seeing here. So this use case is around automated miniature robots using an indoor voxel map to position themselves. So what we see in the bottom screen is the voxel map. So we went inside and we first built the voxel map of the interior space of this office. And then the two top screens are actually the cameras from the robot. So the one on the left is the RGB values. It's what we're used to seeing. So as the robot is moved through the scene, and what you can see on the right is the depth camera doing all of the recognition. So what's happening here is it's recognizing pre-mapped voxels. So that the AMR, the automated miniature robot, has a copy of the voxel map internally and can compare the voxels around it to triangulate its position. So we can do this in completely GPS-denied environments with centimeter-level precision, not just in terms of the X and Y axis, but the Z axis as well. You'll see this as they're going up the stairs. So it's a really powerful technology, actually, for enabling automation and robotics inside. And this whole model is exactly the same. It's the same model that we're using for mapping the outside of buildings and cities, in the country. The same technology is being used inside to create this interior map as well.
All right. Thank you, Peter.
No problem.
It gives you an idea of what can be done internal to buildings, et cetera. So back to the outdoors. So in terms of utility assets, so many times utility assets are in the right-of-way of the transportation corridors. Sometimes they're not, but many times they are. So this is a project that we performed doing utility infrastructure asset capture, actually using aerial LiDAR. So we partnered with an organization that collected the data, and then we did the data processing of all this content, and then used the VAM software to do all the AI ML-based automated feature extraction. So we did some additional training of the algorithms on these particular transmission assets, and then validated that, and then did the feature extraction. Another area is like vegetation encroachment. So, this one here is for a utility, but it could also be in the transportation sector where, the vegetation is growing, out and over a road. But in this case, we did the data collection. As you can see, the top image is the image, the RGB image of from the Symbo system. The middle image is the RGB values attached to the voxels that we collected, the LiDAR, and then the bottom one shows vegetation encroachment. So different colors are different distances from conductor lines. So you can actually identify, the amount of vegetation around a conductor line, create that vegetation quantification, generate a report of those particular voxels and the location of those, and use that for vegetation management, like work order monitoring, and their work order management systems as well. Change detection. Change detection is a pretty common theme. And so in this case, we had collected the area in San Francisco, so we had the base map already collected, and the customer was interested in identification of new 5G antenna assets on poles. So we did the post-installation collect, and then use the AI and ML-based automated feature extraction to extract those antennas, and this helped that particular customer in the validation of contractor work orders. Okay, so pretty valuable to them, and really all they wanted was identification of where that asset was, what the asset looked like, and the geographic location on that particular pole. Make sure that it was put on this pole, not on this pole. Right? And then we've done some work as well in the 5G signal mapping and attenuation. So in this case, we drove a city, and within that city, this particular customer within the telco space had 5G asset antennas. And so from those, we could had generated signal attenuation models and then voxelize that in 3D space. And so then, the top image is an aerial view of the data we collected. The middle one is basically driving the street, and those individual voxels in the air there are, 5G signal propagation models. And what we've done as well is we also collected data internal to their structures, their own buildings that they own. And then you can do the same thing there. You can actually walk the building or look at maps of the building internally of where there is 5G signal strength or where there's dead zones. And so that helps them in identification of areas where they need additional infrastructure to support that. This was a recent POC proof concept that we did with a telco. And so if you think about the process to actually create maps for vehicles, right? So we did a road data collection of an area of a city. And so the data collection and harvesting, we used our HD mobile mapping symbol system that Peter talked about earlier. We then provided the physical hard drives were then shipped to a data center. Data center can process those, do all the corrections, data alignment, if you require PPK corrections, et cetera, the merging of the voxel data, and then doing a feature extraction and the vectorization of that, and then creating that HD map. That whole process takes about 1 to 2 weeks. And then that's provided to the contractors who then provide that data to the vehicles out on the street. And that whole process is about a 5 to 6 week process. So it's it's short in the whole scheme of things. That's pretty short, but for certain applications, that's too long. So what we did was we teamed up with Verizon and AWS, and we have the exact same collection, except at this time we have a Wi-Fi device on the Simbo system. So the data is collected. We're passing the LiDAR data to via the 5G network, the 5G Edge network from Verizon, and that is then delivered over the 5G network to the Verizon center, their facility, which has an AWS wavelength instance, which is basically an AWS Mac at Verizon. So it does the processing right there with incredibly low latency. We then create the 3D model, do the extraction, build the HD map, and deliver it to the vehicle, back to the vehicle on the road. And the turnaround time from the collection to the vehicle having a full 3D model was 15 seconds. So pretty average 15 seconds, I should say, but pretty incredible time reduction. And, no doubt both AWS and Verizon were incredibly happy with this. And Peter was part of a presentation at the Mobile World Congress in Barcelona last month, describing this proof of concept and application. So what I wanted to do was talk a little bit, because there's a lot of money available or to be available in this U.S. Senate infrastructure bill, specifically for road infrastructure. So I just thought I'll share with you a little bit, but we're putting together a white paper that we'd love to share with you that kind of digs into it. So it's not, it's not tied specifically to Voxelmaps. We're just, we'd like to help educate people in terms of the opportunity that exists within this. So this House Bill 3684, it authorizes funds for federal aid, highways, highway safety programs, and transit programs, and for a lot of other purposes, as we well know. But in reading that full text, you can go ahead and read the 2,700 pages if you'd like. But what we've done is we're pulling together a white paper that pulls out the key components for those of us involved in the geospatial realm. But there is significant emphasis in this bill on geospatial modernization and innovation. So this just, it's a 1.2 trillion over 8 years. It's a lot of money to spend. But if you look at these people on this call that are interested in transportation, this is us, right? A lot of it is what we do within the transportation sector. So lots of opportunity out there, and we'll kind of dig into some of these numbers in the white paper and provide that to you as well. So an interesting thing is that, excuse me, when you read through the bill, the terms digital twin, digital cities, virtual reality, augmented reality, they're not highlighted in the bill, but I think they're probably, they're too specific to mention in the bill, but they represent a really solid pathway to fulfilling the goals that the bill otherwise outlines so well, right? So there's opportunity. They don't talk about digital twins, but, the underlying technology I see is this, the whole voxel technology, basically. And, one of the areas is, the digitalization of construction. And that's going to be, that has to be very rich in the 3D environments for design and construction and that whole infrastructure life cycle. So we really feel that the bill may be a catalyst for many organizations to finally take that full 3D and 4D plunge, right, into using the technology in a pretty wide way. All right. So Peter gave us an overview of Voxelmaps as an organization and the significant history of the organization that we have in performing LiDAR and visual mapping. He then talked about the concept of maps for machines and a bit about volumetric mapping 101 and and the way that we do it, what we see in terms of volumetric mapping in this whole 4D volumetric space. Talked a bit about the SIMBO and our data collection and how we go about that. And then the 100 cities, the DAS data set that we've just recently embarked on in terms of collecting data across across the 100 largest metros in the US. I provided an overview of some of the use cases, potential use cases across the transportation segment, as well as a number of other industries. And then a brief overview of the Senate infrastructure bill that everybody on this call should be interested in. Like I said, we'll be putting out a white paper in the near term that will definitely get in your hands, and I think you'll find it very valuable. So with that, I'd like to open it up for questions, and I'll just say if anybody has any specific questions that they have that they don't feel comfortable in sharing with the group or asking to the group, you can reach out to Peter and I at our contact information right there. But let me look. Is it possible to find the weight and volume of vegetation with this technology? So I would say the weight probably not. The volume of vegetation, yes, because we're measuring. Each voxel has a measurement structure and has a coordinate to it, and so in that volumetric model that I was showing in terms of the vegetation encroachment, you can run a report and export a CSV showing all the voxels within those certain segments or distances. Question says, your slides have the noise removed, especially those involving transportation. Are you going to have slides showing your process to remove that noise?
I can answer that, Brian.
Okay.
Yeah, so it's a really good question, actually. So there's two aspects of noise. There's obviously noise just generated by the LiDARs themselves. And there's noise, when you're trying to merge multiple passes of data together, multiple point clouds, and obviously convert into voxels. That approach, that's all done in our processing pipeline. We use a lot of advanced SLAM technologies to do that, so simultaneous localization and mapping for doing it. But in particular, when you talk about noise from things like cars or people or traffic that we don't want, we use deep neural networks to do that. So we actually identify cars using AI, and we extract those from the data set. So you'll notice there were no cars, people, pedestrians, cyclists, pets, etc. That's all done thanks to the AI and the deep learning.
Thanks. So here's another question that says, our DOT service area is quite large. What's the largest area you have been contracted to collect? So last year, Voxelmaps collected over 650,000 miles of roadways across Canada and the continental US. So a pretty significant amount. That's 650,000 miles is about 50 times around the Earth at the equator. So a lot of driving, a lot of windshield time. Here's another question. If using data from multiple sources collected via different vendors, what sorts of challenges do you encounter calibrating those at scale so that you get them to align with our universal reference system?
Yeah, no, again, a really good question. So we're used to ingesting data from many different sources as well. Clearly, we have our own sensors, and they're all pre-calibrated, and they work seamlessly with our model. But at the same time, we can ingest from other mobile mapping solutions, other fixed solutions, or pedestrian mapping, where you have backpack solutions, and also aerial LiDAR as well. So we've done a number of scans. A few weeks ago, we just finished scanning San Francisco from the air using a helicopter and aerial LiDAR as well. So there are a number of parameters which we need to do calibration. So generally speaking, when we're working with somebody else, we'll go through that. It's really just an understanding so we can make sure that we correct for those things when we import. So there's a little bit of manual work in the beginning just to make sure the calibration works. And once that's set, then the ingestion happens pretty seamlessly.
Okay. And then here's another question. How are you going forward with processing in areas that do not have 5G connections, such as in rural or national park areas? And I would answer that in saying that we don't, to do the collection and processing, it's not required to have a 5G connection. So that 5G connection that we had for that POC, that proof of concept, was for a particular area with heavy 5G coverage.
Yeah, so just adding to that, so each of the Symbos have SSD drives in them as well. So everything is stored on the SSD drives. Typically, in the old way of processing, we would just take those drives out and plug them into our data center and essentially ship them to the data center, and that would be the most efficient way. If there is a 5G connection, obviously we can offload with 5G, but clearly in a national park area, that's not going to be likely. So it would be the standard approach of writing to the hard drives and swapping the hard drives out.
Okay. You somewhat answered this before, but I like the high definition maps you create with your Symbo system. However, I also need to collect top-down views of some of my assets. How can you collect both? And that's really no problem because we have strategic relationships with both manned aerial and UAS-based data collection organizations. So we can, as Peter mentioned earlier, we consume a wide variety of rich sensor content and from various platforms and use that within the VAM software platform. So, we could be the single source and do the driving, the mobile collection, as well as contract with organizations to help us with the aerial. As Peter mentioned, we actually just completed the San Francisco area, both driving and with a rotorcraft with helicopter. Another good question. So how much processing are you doing on the edge? Just the initial LiDAR, running ML models and calibrating to your system, all the way to extraction and deliverables. So you want to address that?
Sure, no problem. Again, good question. So on the edge, the primary thing that the system is doing there is what we call the sensor fusion. So it's taking all of the information from the LiDAR, from the cameras, from the IMU, GPS, etc., and fusing that into what we call a voxel stream. And then it's that stream which is then either sent directly to our private cloud or shipped essentially in the hard drives. It is doing some calibration. It is doing a little bit of SLAM as well at that stage. But the bulk of the ML and the extraction happens in post-processing within our cloud.
All right. And then there was a question early on about the presentations, and the person liked the presentations. Do you offer documentation for PDHs? So currently we do not, Charles. Okay. And then the last question that I see here is about pricing. It says, how do you price your content? So pricing is pretty broad in terms of how we can price. So it's really based on customer requirements. So do you need it via DAS or an FTP? Do you want full ownership, or you just want to license the data for your extraction purposes? And then we can do it many times is by linear mile in terms of the collection, but also we can do it by the number of assets that we extract. So if you're just looking at, I just want the roadway, by linear mile, we can certainly price it that way. So we're pretty open to pricing the product really any way you want. What countries are you operating in? So I mentioned before that we did collections last year in US and Canada. So far this year, I know we've been in Australia, we did Singapore, Hong Kong, I think Slovenia. Peter, any other countries that we've collected in already this year or in the near past?
Yeah, so so Voxel specifically, we're active in about 26 countries now. So the biggest ones are still North America, but as you say, across Europe, into Asia, Singapore, Hong Kong, Australia, a little bit in Latin America as well.
Okay, cool. Well, we're coming up on the hour and there's no further questions. So we really appreciate, Peter and I appreciate you taking the time today to listen to our presentation, and hopefully we've sparked some interest in terms of what we could do together. We'd love to talk to you further about some of the projects you're working on and how we can support some of those applications. And as I mentioned, we'll be reaching out to you as well with this white paper on the infrastructure bill, and hopefully that'll spark some interest in how we can help you in that capacity as well. Thank you very much. Cheers.
Thanks, everyone. Bye-bye.